There are many types of hazard analysis methodologies out there, but today we will talk about one of them which had been widely accepted and applied in the industry, and it's called HAZOP, which is Hazard and Operability Study. This methodology had been developed by ICI in 1960. In a nutshell, what we need to do is to identify the hazards and operation risks. And then after we identified those risks, each one we need to identify the consequences and if we have a safeguard for such risk. If we can't find any risk or we feel that we need more of risk safeguards, we can put in this study recommendation for the engineering party to go and study more and see if they can add more safeguards. Should we do HAZOP for each and every project we do? In fact, some of them it's well established that we need a HAZOP. In oil and gas, petrochemical, HAZOP is a must. But some other processes we may not need a HAZOP. But if you are in the project stage, you can't assume that we don't need HAZOP. So we go into something we may call it preliminary hazard analysis. In the hazard analysis process, we study the process and we came to a conclusion that we don't need a HAZOP, or we need to limit the HAZOP to a specific set of stuff, and we go from there. Why we go into the PHA and go into a full HAZOP? Of course, two things: cost and delivery impact on our project. HAZOP is the first step in identifying the safeguards, and after that we go into safety instrumented level study, which is the SIL. In the SIL study, we identified that the safeguard we have is adequate enough for the consequences that will be developed. Any project goes through a specific, and if you can call it, stages: design stage, construction, and operation. During design phase, we may need to do a HAZOP on 2 times, one in the conceptual design or in the feed, and one in the detail. So sometimes they call it feed, front-end engineering design, sometimes they call it basic design, but normally we have one HAZOP in the feed and one HAZOP during the detailed design. When the plant is in operation every 4 or 5 years, we may need another HAZOP. Why we need a HAZOP? Because we gain a lot of experience about the project. We have seen much of the process in action, and we may need to add more stuff to the safeguards or remove some equipment, add some equipment. We need to study the impact of such addition or subtraction of the process. So what we do? The first we need something to go by. We need a guidelines. We sometimes call it charter. So in the charter, we need to list the scope, rules and responsibility, who's going to attend, the schedule, the software, and the document list. And we know that we need to add more stuff also. Who do the charter? It's not in the engineering company, but normally if it is a big project, then we hire a specialist who actually do the charter. Then they send it to the project who accepted it, the project meaning the engineering company and the proponent or PMT to accept the charter. And then after that, when we do the HAZOP itself, we bring some document with us, the charter of course, P&ID, PFDs, cause and effects, layouts, area classification, and we may need more equipment drawing. What stage of drawing we need to use? It's ideal if we can use the final drawing, final PNID, final process flow diagrams, or issued for construction. But during the study, we may not have those documents. So we will do the HAZOP with well-developed document, but when the final document is finished, we do a gap analysis and we check what had been added or removed from the PNID or the other document, and then we can initiate and flag to the project that we have some places we need to revisit our HAZOP. Let's go into some of the rules and the assumptions which could be in the charter. Of course, this depends on your project and your process. So one of the items which is always we use is two risks cannot occur at the same time, meaning a double jeopardy. We don't study the double jeopardy, meaning two risks will be happening simultaneously. Other assumption is that the operator who runs the operation is well trained. Our operator is well trained. If your operator in the control room, then we allow 5 minutes for him to do the action. If he can't do the action within 5 minutes, then we accept it as a safeguard. If the operator can do this in the field within 20 minutes, then again, this is acceptable behavior, acceptable safeguard. Meaning, if your operators in the field need to go and open a drain, stop a pump, or something like that, and happens within 20 minutes, then it's acceptable. HAZOP is not a PID review, so this is one of the rules. And our focus during the study is to identify the issues, but we are not attempting to solve or redesign the process. Some other rules and assumption that the safety relief valve are well calibrated in their times and they are closed during normal operation and so on. So you put here all the assumption you think that the guys during the HAZOP should follow and restrict your activities within these assumptions and rules. The scope is the boundaries of your HAZOP study battery limits. So we should have maybe in the refinery, if you have many more areas, a lot of areas, you can concentrate on one area and one plant, another plant, and so on. So you may do it all in one session, meaning may you stay for a week or two or a month or more. And then if you missed something, you may need an HAZOP for the interface between those two areas. Who are the attendees in the HAZOP? The first one is the facilitator or the leader. If you have a very tiny piece of HAZOP or follow-up, you may have someone from the engineering company acting as a leader or the facilitator. But if the whole process, you may better to have someone who has some good experience with a HAZOP process. Mainly you have one represents safety, one represents process, one represents INC. From the operation, you need one also. So the engineering company and PMT or the owner, you need one of those categories. Do you need electric or mechanical engineers? Well, we need them, but this is on-call basis. So if we find that we have a package and we need a mechanical engineer who explain to us and go through the package for us, then we call for them and they can come and help us as the electrical engineer as well. So in the charter, we define keywords or guide words. And then those guide words are pressure, temperature, flow, level, and so on. And then we say, what is the risk if there is a deviation in the pressure by going very high or very low? So our deviation would be a pressure going high, temperature going low, and so on. So the first step is to define the keywords and the modifier for each one of these. So you take one of the guide words and put a modifier and see what the causes which can cause the pressure to go high or the pressure to go low. And then you list all the causes. And once you finish them, you go into the next step. So don't go and take one cause and go horizontal. We go vertical here. So when you list all the causes for the pressure to go high and the pressure to go low and the temperature to go high, the temperature to go low, the flow and the level, you listed all the causes. You go ahead and look at the consequences for each cause of them. And in general, the consequences could be equipment damage. So you will specify which type of equipment, and if you can specify which equipment damage is there. So if we can say pump damage, we may say also pump shaft damage. So the first one is equipment damage, the second is production loss, and then personal injury or fatality, environmental losses or impact, and then we have a contamination which may lead to an off-spec product. Now, after you look at the consequences, you take each one of the consequences and then look at if you have any safeguard associated to stop or prevent or mitigate this cause. In general, again, most of the stuff you can say, I have a mechanical safeguard. I have a safety relief valve which prevents the pressure to go over and beyond the design. You may say, I have non-return valve that is a pure mechanical. And then you can say, no, it's not. We need two in series because normally non-return valve leak is about high, it's about 10% or something. Then it's not acceptable. Then you need to add more. You can rely on your control system to take an action. You give an alarm, or you can stop a pump, you can open or close a valve. Or you can rely on the operator to take an action. You can take an action in the control room. After the operator receives the alarm, he can do some action by himself or send someone to the field to do some action. So once we did this, we looked at the causes, the consequences, the safeguards. We may decided that we need more action here. Then we put a recommendation, and this recommendation is considered points that had to be closed by the engineering company. Closed meaning either apply alternative, or say, no, we can't do it as you want, and this is the causes, and we propose to do this. One of the tasks the facilitator should do is defining the nodes. So the node is a part of the process that need to be addressed together. So node 1 is before XV1. Node 2 is the yellow highlighted, is starting from XV1 valve and include the tank, the pump, and the heat exchanger, and also XV2. Node 3 is the distillation column and downstream of it. Then we only consider when we study now is node by node. So node 2, we look at node 2 and see in node 2 what can cause node 2 high pressure or high level. If you look at the tank, you find two level transmitter. One of them has high and low alarms, The second has high, 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 low, and low, low. Normally, high, high, and low, low is associated with trip function or save function, open a valve, stop pump, and so on. The high and low are associated with alarms. And sometimes you look at the designation of this bubble, and some of them may be a safety system, some of them is another PLC or something. So you also understand what is going on here, not just the action, but what kind of equipment you are talking about. So now we look at one deviation, which is level low, and we considered this tank. That is the only place we have level. So this is the only thing we need to address in the level low. What can cause the level to go low? If the valve XV1 is failed to open upon request. So the problem is not the valve is closed, but the problem is the valve refused to open. So this could be the valve stuck, could be the control system failure, and so on. Other thing is this loop, which is controls the level here. So it measures the level in the tank and control the control valve opening to allow the level here to be stable within our normal operating point. But if the transmitter reads wrong, or the valve refuses to open, or the control system have a problem, then the loop will fail. In this case, we call loop LIC-1 failed. Failed in a manner to cause the level to go low. But it also can fail in another way that makes the level go high. So we will consider it also in both cases, in level low and level high. Each one of those causes, we will put the consequences. The consequences of the level being low, this pump could cavitate and can damage. So we can say pump damage or pump cavitate / damage. Also, your production will stop because you don't have enough liquid or something in this level tank in the tank, so you have a production loss. Once you finished all your causes of the level low, you can look at your safeguard. The safeguard here are the level alarms and the action from the control system to stop the pump. Now this transmitter is associated with the control system or the SIA system that trips the pump. But if this one is failed, then your control system will not be able to trip your pump. That means I can't use the control system as a safeguard in the case of failure of this transmitter. And this high and low level alarm, I cannot use them to tell me that we have a problem with this loop because it is failed. But I can rely on the alarm coming from this transmitter if this loop failed, and I can rely on this alarm high and low if this transmitter failed. But think about if you have only one transmitter, what would be the scenarios? So in this case here, we have to list all the safeguard and make sure that we have safeguard for each cause of the causes. As we said, the safeguard could be safety valve, and we assume the safety relief valve are well calibrated and working fine, and it's closed. And we said that we do not consider non-return valve. It's only if there are two of them in series. And we looked at the control action, which is can open a valve, close a valve, and or give us an alarm. The operator action, sometimes we say there is a pond which is very far away. We don't have any instrument to measure and tell us if we have overflow in the pond. So we said in this case, do we have a field operator goes and check on this pond? They will tell us, yes, there is one every shaft. In the beginning of the shaft, they go there. That is part of their normal routine. So we can consider it as a safeguard. If none, then we say we need to add in the operation manual that an operator needs to go there for in each shaft twice or more to check on the pond. Once we finish the high level, we go into low level, high pressure, low pressure, and so on. So far, we talked about the risks, but we did not rank the risks. You can't assume that damaging a pump which costs $10,000 is equivalent to damage a pump which costs, let's say, $500,000. So we have two things will help us to put a dollar value for each one of those consequences. One is the probability of the deviation to happen. The second is the severity of the consequence, meaning one is the less probability to happen and five is higher probability. So assume we talk about freezing water in a pipe. If you live in, let's say, in the north, then you may have a very low temperature once, twice, 5 times a year, or never happened. So you can go and give you the proper number here in the probability. Then the severity. Now, if your pipe has water and this pipe the water freeze, then the pipe would burst, then the severity will be high. And the impact on your process, you can look at the impact on the freezing pipe, the damage of the pump, and so on. You can look at them and see if something is costs you a lot, but could happen once a year or once every 10 years. But sometimes you have something costs you less, but can happen frequently, more frequent. This we can look at them as a higher and a medium and a lower impact on your process. Finally, there is more data on the web. So please do your homework. And here is some handbooks. You can see it in the US Department of Energy. They have listed more resources. And also you will find more and more on the web. Please, because it's very important to know why we need to learn about HAZOP and to make sure that the HAZOP is done properly. In the next video, we will have one very important thing, which is what could go wrong with HAZOP. Finally, thank you, and there is more in the playlist all about INC and the link in the description. Appreciate if you like, share, and leave a comment.